This is lecture 13, part 3, and in this particular part I'm going to describe some color mixing properties, behaviors, derive Beer's law, and then finally introduce the systematic specification of colors, namely the color systems of Ostwald, and then refer you to other color systems that are used today. Just briefly, I want to review that in parts 1 and 2, I introduced 3 terms that are going to be relevant in this particular part, namely that of hue, H-U-E, which is a term used to describe or refer to colors as we perceive them. Value, which is a term that refers to the relative lightness of a given hue. And finally, chroma, which is a term used to describe the saturation or the impact a given hue has perceptually. In part 2, I introduced the results of a psychophysics experiment, namely the relationships between certain colors pairwise based on the effect they have on your mental impressions. So there were 2 complementary pairs, namely blue and yellow and red and green. And then in spite of the vagaries, shall we say, of the sensory impression, there was also an experimental method of demonstrating the complementarity, namely the spinning color wheels. We look, however, at those 4 colors and we realize that we only need 3 of them, because as it turns out, if you start to superimpose projected light, namely light that's red, green, or blue, and combine them, you can make yellow by combining red and green. So yellow is superfluous as a primary, and namely that if you also add blue, you get white light. So the upshot is that you can create any hue by combining light of these 3 primary colors, and this is the definition of a primary color. Recognizing that we can create any hue by combining any of the primary colors, we can distinguish between 2 types of mixing processes. The first of these is additive, where you blend combinations of red, blue, and green light, and this can be seen using the Ratten filters. And so if we look at a purely red light created by a Ratten filter, we realize that we're transmitting light above 600 nanometers, so there's a cutoff. So this is an absorbance plot, meaning that everything down at the bottom is what's being transmitted. If I now look at or combine the red filter with a green filter, we get with the green filter components that are above 600 on the right-hand side, plus an additional band in the 500 to 600 region. So that when we combine red and green, what we're doing is allowing in other words, red and green light, not filters. This is red and green light projected. We get a total of the 600 and up plus an additional 500 to 600, and so you get yellow light. So by combining light from projection lamps, that's red and green, you get yellow. I just want to be clear on where the light is coming from here. In contrast to the additive mixing, in which you're adding light of specific bandwidths in combination, there's subtractive mixing, in which you selectively remove bandwidths from an existing light source and create different colors. So you take colors out of a light source or incident light. The filters themselves form a triad, much in the same way as you have a triad for the additive mixing. So instead of the red, the blue, and the green of additive mixing, you have yellow, you have magenta, and you have cyan, which is a kind of greenish blue filtering system that can take out specific bandwidths. And this is best seen by looking at some of the Ratten filter absorption spectra. So first, looking at the cyan spectrum, the cyans absorb specifically in the red, and so they will remove red from the light source, leaving you with green and blue. If you have magenta filters, they take out the center of the visible spectrum and leave you with blue and red. And then finally, if you use the yellow filter, you can take out the blue and leave behind the green, the orange, and the red. So in combination, you can make colors selectively. So the background in this cartoon is white light impinging and being intercepted by the three filters. The magenta is on the top right, the yellow obviously, and cyan rather is on the top left, yellow obviously, and the magenta is at the bottom. And note that when you combine all three and compare that to the spectrum I just showed you, you are effectively removing the entire visible wavelength, range of wavelengths, and essentially block the light. And again, this is from the Kodak website. Subtractive mixing is the process that occurs when you paint with pigments. So the pigments absorb light specifically and reflect only what is not absorbed. So they are essentially taking light of a specific frequency out of the incident light that gets reflected back to you. And by combining the pigments, you can replicate the effects that you have in the previous slide, namely the removal of light in total when you combine cyan, magenta, and yellow. Subtractive mixing brings us naturally to the discussion of absorption of light and the quality, the property of transmission. So we'll begin by introducing transmission, and we'll refer to light being unchanged as it goes through a material. So initially there's no absorbers. You can just think of this along the lines of glass. So the first thing that happens as light enters a medium from the air or a vacuum is that it's slowed down. So the velocity of light changes according to the nature of, you can think of it as the density of the material through which it passes. And we define the refractive index as the ratio of the speeds of light in the two media. If the light hits at a normal position, namely perpendicular to the surface, it goes through straight. If it comes in at an angle, the angle changes, and so you get the dispersion of light according to wavelength that is familiar to you as the prismatic spectrum. In contrast to that, if the medium contains absorbers, namely pigment materials that specifically absorb light or absorb all the light, in fact, if it's neutral density or black particles, you have what's known as absorption, and the light intensity changes as a result of passage through the material. So we introduce this using a representative example, the properties of the material. So we have an absorber, in this case represented by a blue three-dimensional square. And in our example, we're going to say that each one of those squares attenuates the light by 50%. So it allows 50% of the light to go through. It can be any arbitrary percentage that you want. So that if we combine three of those filters or absorbers, each stage reduces the previous stage by 50%. So we go from 100% to 50% to 25% to 12.5%. And by examining those behaviors, we can rationalize what will eventually become the Beer-Lambert law. So the first thing to consider would be taking the same density of pigment and putting it into an absorber that's 3 times as thick, and you would get the same effect as if having 3 absorbers. Similarly, if you took the absorbers, namely the number of absorbers in each of those units, and combined them into a single unit, what we're doing is saying is a rather roundabout way of saying we increase the concentration by a factor of 3, we similarly get the same effect. So you increase the density of the pigment by 3-fold, you achieve the same effect as if having 3 independent filters. And so those two facts together give us what's known as the Beer-Lambert law. And there's a caveat, however, to the Beer-Lambert law, and that the material must not scatter. And we'll describe scattering in a couple of slides to go. If I re-examine the previous slide, namely the attenuation of light in 3 stages, I can make some statements about the mathematics that I want to use. So in the previous slide, I said I can get 3 times the effect by making tripling the wavelength, or tripling the path length, or tripling the concentration. And the percentages there would be something I would define as the transmittance, namely the ratio of the light that passes to the initial light that enters the absorber. So with that definition, I realized that I would have to multiply each percentage. So the transmittant would be multiplicative as opposed to additive in this case. So it's a geometric progression, which is a little bit inconvenient. However, if I take the log of that ratio, namely log of the transmittance, that gives me a number that is additive. And you can do this at home with your calculator. So take the percentages represented as fractions, take the log of the percentage. So if you take the log of 50%, you come up with something like 0.3. And then the total absorber, the log of the total, namely each stage would just be adding 0.3, 0.3, 0.3, as opposed to multiplying 0.5 times 0.5 times 0.5, which seems like a trivial point at this stage. However, that when you want to relate this to the concentration and path length, the additive measure works out better for you. You don't have to multiply the same number times itself, so you're not working on a square law, you're working on an additive or multiplicative law. The log, however, since the transmittance is a fraction, the log comes out to be negative, but you can fix that by defining the absorbance as the negative log of the transmittance, and thereby establish that the absorbance is proportional to the concentration times the path length. The proportionality factor we're going to see a little bit later is the extinction coefficient, or the molar absorptivity. I mentioned scattering previously, and scattering is the wild card in the absorption of light phenomenon. So as the wavelength of, if you have particles suspended in a medium, and the particles of the pigment, in this case, have a finite size, they can start to scatter the light rather than simply absorb it. So they could scatter light of a different wavelength than the absorbed light, simply because as the wavelength of the light starts to match the physical size of the particles. So you get scattering effects as a result. The mechanism can be described differently depending on whether you want to talk about classical mechanics or quantum mechanics. You know, arguably, in the case of quantum mechanics, the light, you would say that the light is temporarily absorbed by the particle and then re-emitted in a random direction. Doesn't really matter at this point. So we introduce additional terms when a medium does scatter light. We refer to translucence as a situation in which light is both transmitted and scattered, and then translucence would make a transition to the opaque as the light is both absorbed and scattered. There's a relationship between the scattering angular distribution, in other words, how much light goes off in a given direction, and the size of the particles in the medium. And this is used in polymer chemistry in particular to estimate the molecular weight of a polymer. Relationship-wise, if the refractive index of the particles differs from the medium in which it is suspended, the effect is more pronounced. So this is something that occurs when you try to make a mole in IR spectroscopy. You want to match the particles' refractive index with the medium in which you're going to suspend them. So this graph illustrates the effect. So as the refractive index to medium, the ratio of the refractive indices of the medium and the suspended particles differs from unity, you get increased scattering in both directions. And so, inspired by our friends, the color kittens, we'll proceed with some systematic definitions of color. Here I will reintroduce that wheel of color that I had in part 2. So again, just to refresh your memories, we took the two complementary pairs, set them up as axes on a circular pattern. So red and green on one axis, yellow and blue on the other axis. And we started making intermediary colors. Color kitten catastrophe is one example, to fill in the regions, the quadrants between the complementary pairs. I want to first address one aspect of this color wheel and answer the question, why is it a wheel to begin with? And the reason follows from the sensory impressions the colors make. So if you look at the spectrum and correlate the color with the frequency on one hand or the wavelength of the light on the other, you have a progression. So in going from red to violet, you are going from longer to shorter wavelengths. If you go from the blue to the red, you're going from low to high frequency. And so you'd be tempted to make a progression through the spectrum and make an analogy to harmonics in sound waves. However, as you go through the spectrum, say from red to violet, you wind up sensory-wise back at the red again, because violet at the other end of the spectrum very much resembles red. And so Ostwald and Newton noted this, and they decided to make the colors arranged in a circle rather than a linear progression. So now what we can do is arrange the color wheel, the wheel of hues, as a kind of two-dimensional polar coordinate axis, and add to that a third dimension, namely that of value, by running the grayscale perpendicular to the plane of the color wheel, as we would call it. And so we have now a three-dimensional system, or coordinate axis set up. Note that we have to match, or at least position, the plane of hues, the colors, so that the values of the colors match the value of the grayscale in the center axis. And now if I look at, say, a cross-section of that three-dimensional coordinate system that I had on the previous slide, I have a color, and then I have the grayscale to the left, and I can now add increasing amounts of white to that color until I reach pure white. So I go off in one direction. If I start and add black to that color, I can make transitions to black along that. So I make these color triangles as a result. And then once I have the triangles, I can fill in the space between by adding grays. And then once I have filled in the grays in a similar fashion that I did in the previous slide, and move from the gray to the pure color, I am defining different levels of chroma. As a result, the triangles formed by the hues on opposite sides of the color wheel give you a pattern similar to the following, and it just remains the systematic definition of what the little chips in the triangles mean. So you have these little designations that indicate the hue and the degree of lightness for each chip or square in the color scheme. And if you take the aggregated components of the color wheel and value triangles and arrange them around the polar axis, you wind up with a three-dimensional solid figure, and this is the Ostwald system of color definition. There are other systems, more modern and redefined. So the Munsell system is a very popular version. The Optical Society of America has their own color system. And then there's an early one by Ridgway, which is very interesting in the sense that he based his color selections on natural colors, namely the colors of birds or the colors of geological materials. And they're interesting from that standpoint. And finally, just a limited bibliography of some of the materials that I used to create this set of this lecture 13.